Okay. So an empirical formula, by definition, is the smallest whole number ratio of the moles that makes up a compound. That's the definition. So it's the smallest whole number ratio of the elements by moles in the compound. So there's two ways that they can give you problems. They can either tell you, here's the percent composition of this compound, figure out the empirical formula. Or they can tell you, this is the number of grams of carbon, and this is the number of grams of hydrogen, and this is the number of grams of oxygen. Figure out the empirical formula. So there's two different things they can do. They can either give you the percent composition, or they can give you the actual number of grams. And then what you're gonna do is you're gonna follow through on a list of steps on how to get to the empirical formula. So the example that is in the book is, the first one is on page 345, and it says, methyl acetate is a solvent commonly used in some paints, inks, and adhesives. Determine the empirical formula. So that's what mine will say on the test. Determine the empirical formula for methyl acetate, which has the following chemical analysis. It's 48.64% carbon. It's 8.16% hydrogen. And it's 43.2% oxygen. And that's it. So right away, you know that this formula is going to be C something, H something, O something. And they want you to figure out what are the subscripts. By definition, the empirical formula is the smallest whole number ratio of moles. These are not moles. These are percentages. But you did the percent compositions, and you did them from masses. So what we do when we see the percentages is we pretend that we have 100 grams. So if we have 100 grams of this substance, whatever it's called, how many grams of carbon will we have? 40. Exactly. So we change all of these percentages into grams. We pretend that we have 100 grams. And then this is what I mean by these problems being a culmination of the entire chapter. We're looking for moles. You know how to go from grams to moles. It was like the very first thing we did. So the very first step is to change all the elements into moles. Stick them all over one. And if you want to do them one at a time, that's fine. I don't know. I do assembly line process. So I put them all over one. I want moles. Moles goes in the top. Change them all to moles. I'm trying to get rid of grams. Grams goes in the bottom. And like I said, you can do it one step at a time. This is like the very first homework assignment. Like one problem would have been, how many moles of carbon is in 48.6 grams of carbon? That's like the very first day. We're just doing it for 3 different elements to get to an end result. So in front of moles, this is the big conversion. In front of moles in the big conversion is a 1. It's a 1. Grams, I get off the chart. So carbon is 12.01. Hydrogen is 1.01. Oxygen is 16.00. 1 mole of an element is equal to its atomic mass. I do math. .64 divided by 12.01. Keep your 4 significant digits. It's very important in these. 4.050, and that's moles of carbon. 8.16 divided by 1.01. 8.079 moles of hydrogen. And I know that should be 3 significant digits, but just bear with me. And then 43.2 divided by 16. Is 2.7, I think. Let me try it again. No, it's 2.7. Are we good so far? We change them all to moles. Okay. The definition for an empirical formula says that it is the smallest whole number ratio of moles that makes up the compound. These are moles. They're not whole numbers. They're not whole numbers. It's a ratio. It's a 4.05 to 8.079 to 2.7 mole ratio. Those are not whole numbers. So I need to make this ratio whole numbers, which is why I do step number 2. I look at what I have over here and I divide by the smallest one. All of them. Maybe this will make a prettier ratio. It will for this one. I've got 1 mole of oxygen. 8.079 divided by 2.7. 2.9999, that's enough for me to round to 3. You gotta be real careful with your rounding. When I did this math, I got 2.99, that's enough to round to 3. 2.75 is not enough to round to 3. 2.99, that's good. So this is 3 moles of hydrogen. 4.05 divided by 2.7, 1.5. 1.5 is not good enough to round. This is another ratio. It's the same ratio, I've just cleaned it up a little bit, but it's still not whole numbers. So this is when sometimes I have to do number 3. If the ratio is not the simplest whole number ratio, multiply them all by 2, or multiply them all by 3, or multiply them all by the same number so that you get a really good whole number. I have 1.5, 3, and 1. What should I multiply to get this to a whole number? And if I do it to this one, I gotta do it to all of them. So now this becomes a 3 to 6 to 2 ratio. And so now the empirical formula, the ratio becomes the subscripts. C3H6O2. You take the definition and then the math goes with the definition. That's the purpose of math. Theoretical math is all fine and dandy, but we use it in science, and now that you're in upper level science classes, there is just more and more and more and more math. You just have to take the definition and use the math to get the right answer. And it's a system. Math is a system. You should have done ratios in math class. I'm kind of banking on that a little bit. And then this is the little bit of chemistry that we did at the very beginning with the conversions. What questions do you have about this? We're going to do another one. We're good?
There's only one of these on the test?
Yeah, 1. But it's worth 1 billion points.
Okay.
Okay.
Like, how many points was that?
Listen, you are not going to learn things instantaneously anymore. Okay. We're to that point now.
Yeah, I know.
Okay. I can do this easily because I'm 4 million years old and I teach this. That's why I get the big desk. They give you the big desk if you know learning. To get rid of that 1.5. I had to make it into a whole number. Yes. Okay, we're going to try another one. Oh, we'll leave it going. Who cares? No, it'll take forever to upload.